You've already seen sunspots in the planetarium and a little bit about the sun's magnetic fields. So we're going to talk a little bit more about how the sun creates those magnetic fields and what these sunspots are. Sunspots are the earliest observed evidence of the activity of the magnetic activity of our sun. They were first observed with the naked eye by Chinese astronomers in 300 BC. By 28 BC, Chinese astronomers were regularly recording sunspot observations, again with their naked eye, which you really should never look at the sun with your naked eye. I'm not quite sure what they were doing to take these observations. And then they were first observed with the telescope by Galileo in late 1610. So here are 36 sunspot drawings made by Galileo from June 1613 to July of 1613. And you can see that the spots are different. Every spot is different and unique. And at least these spots appear to be kind of in particular bands on either side of the sun's equator. That is a feature of sunspots. So what are sunspots? Sunspots are temporary dark regions on the solar surface. They're created when intense magnetic fields created deep in the sun's interior rise to the sun's surface, intersecting with the region that we call the photosphere. Okay, so here's an image of the sun, taken just the surface of the sun, which is what we can see with what we essentially call white light, taken in April of 2014. Here we have sunspots, these dark little splotches on the sun's surface. And here we have the Earth to scale. So the Earth is about the size of each one of these little sunspot regions. Here is a zoom in of a sunspot. Sunspots have a particular structure. They have this dark part in the middle that we call the umbra, U-M-B-R-A. And then they have this ring around them that we call the penumbra, P-E-N-U-M-B-R-A. And then look, we see more of these convective granules here. That's what we have surrounding here. So what happens is the sun's magnetic field, there are these ropes of magnetism. A part of that rope is poking through the sun's surface right here where the sunspot is. So the center of that intense magnetic concentration of that magnetic rope is going to be right here in the umbra. And then in the penumbra, and that magnetic rope starts to spread out a little bit, start to expand, and then those magnetic field lines, instead of going straight up, start to kind of bend away from the from perpendicular to the surface, and then you get these penumbras here. And so these giant loops of magnetism attached to the sun's surface at the foot points of each one of these is where you will find a sunspot. So sunspots usually occur in pairs because of this, because you have this rope of magnetism attached to the sun's surface. One foot point of that rope is one sunspot, the other foot point is another. The lifetime of sunspots ranges from a few days to longer than a month, and their sizes vary from about 10 miles in diameter to 10,000 miles in diameter. Here's one of the largest sunspots that has ever been recorded, and it's about the size of Jupiter. Okay, so one of the largest sunspot regions. So these can get quite big. So they're dark, these sunspots are dark because the temperatures there are a little bit cooler than the sun's surface average. So the temperatures of a sunspot can be about, right here it says 1,300 to 2,800 degrees Celsius cooler than the sun's average surface temperature. In the magnetic fields concentrated inside these sunspots can reach strengths of 1,000 to 4,000 Gauss. This is what this capital G stands for. Gauss is a unit of magnetism. And that's about 2,000 to 8,000 times the Earth's surface average field strength, which is only about half a Gauss. Now the sun has varied magnetic activity. The number of sunspots on the sun's surface varies over time, as do a bunch of other solar features. Okay, so this is what the sun looked like in April of 2014. We've got a lot of spots. Here we have these spots on either band around the sun's equator. Here we see them again in what we call a magnetogram. A magnetogram shows us the direction or the polarity of the magnetism. So we talked about polarity of magnetic poles and of the magnetic field coming from a bar magnet when we talked about the Earth's magnetic fields, where you have one end of the bar magnet, the magnetic field is coming out in one direction, the other end, the magnetic field is coming in. So you've got one direction of the magnetic field when you see a black spot here, and you've got one direction of the magnetic field where you see a white spot. So you see, so these are all images taken of the sun on the same day. So here we've got the sunspots in a visible light image, and then this is the magnetogram. And so here where this patch of sunspots happens to be, we've got a patch of magnetism, one magnetic field oriented in one direction coming out of the sun, arching over, and then the magnetic field in the other direction here coming back into the sun. And that corresponds with these big loops of magnetism attached to the sun's surface. These big loops of magnetism we call coronal loops. And that's what this image is showing us right here. Yeah, just like the magnetic field coming from the bar magnet. So the black splotches here on the magnetogram, that's a magnetic field coming out of the north end of a, you can think about it as like a horseshoe magnet, arching over and coming into the south end in the white regions, okay? So here's what the sun looked like in November of 2016. So just a few years after 2014, we see the sun's magnetic field has decreased, or at least the number of sunspots that we see on the sun's surface has changed. And we know that the sun goes through a cycle of magnetism on average that reflects in the number of sunspots that we see over the course of about 11 years. And so that's what we call the solar sunspot cycle. And what we see here, so each sunspot cycle lasts about 11 years, with cycles varying in their intensity. So here's an image that shows this number of spots on the sun's surface as a function of time. And you can see that the number of spots changes over time. Okay, so there was a time period in the late 1600s, early 1700s, where the sun almost had no spots at all. But in more recent years, we see the sun's cycle of magnetism, at least as it appears in the number of spots, increases over time and then decreases and increases again. Okay, and so the consecutive time period between consecutive minima, what we call minima in the solar sunspot number, or consecutive maxima in the solar sunspot number is about 11 years. So 11 years between, on average, seeing no sunspots at all to the magnetic field increasing, and then back again when we see almost no sunspots again. And this cycle is not just reflected in the number of spots on the sun's surface, it's also reflected in what we can observe in other wavelengths of light for the sun as well. And so you see that the number of spots on the sun's surface varies over the course of 11 years. And between these consecutive, what we call solar maxima, you don't always get the same number of spots that appear on the sun's surface the following 11 years. So we can also track the sun's magnetism by what we call the solar butterfly diagram. That is a diagram that shows us the position of sunspots on the surface over the course of these 11 years. So sunspots don't just appear at random locations. They are confined in two latitudinal belts on either side of the solar equator. And so these sunspots start to appear at mid-latitudes on the sun of around 30 degrees on either side of the equator at the beginning of what we call a solar cycle. And then those sunspots kind of start to appear closer and closer and closer to the equator over time as we reach the end of that 11-year solar cycle. So here's an example. Let's look at what we call solar cycle 17, which had a minimum in its activity down here, which corresponds to spots starting to appear at high latitudes. And then over time, okay, those spots come and go. Spots don't usually live for longer than, sunspots don't usually live for longer than a month or so. So that sunspot diminishes and new sunspots appear. And then those sunspots that keep on appearing start appearing at lower and lower and lower latitudes. When we reach the most number of spots visible on the sun's surface, actually those spots are appearing somewhere at around 15 degrees around the equator. And then as we reach toward the end of the solar cycle, when we're decreasing the number of spots visible on the sun's surface, then we start to have sunspots appearing at lower and lower latitudes closer to the equator. And then when we start a new solar cycle, we start to increase the number of spots that we see on the surface again. And then those spots in the new cycle start to appear at higher latitudes. So that's one way we know we've ended the 11-year solar cycle, on average 11 years, is when the number of spots diminishes and we start to see spots transitioning from appearing at the equator to starting to appear at higher latitudes. In this plot, we've got the number of sunspots as a function of time. And again, we see that at the beginning of a sunspot cycle, we have almost no spots on the sun. That number grows until it reaches what we call a maxima. And then that number of spots diminishes until it reaches a minima again. The total number of spots you get at consecutive sunspot maxima isn't constant over time. So you see here that in what we're calling solar cycle 4, we had a lot of spots during sunspot maxima. But then in the following cycle, we still had a cycle of magnetic activity, a cycle that we can see in the number of spots. But we see that the maximum number of spots achieved is much less by 200 number of spots on the surface. So we know that, again, the cycle repeats itself on average every 11 years, but it isn't always as strong in amplitude every 11 years. Right now, we're over here at the end of cycle 24 and coming into what we call sunspot cycle 25. We give these sunspot cycles a number or a name so that we can talk about them. With me as a solar physicist, I can talk about the sunspot cycle with my colleagues and say, oh, hey, yeah, in cycle 23, this happened, but in cycle 24, this happened. I know a lot about the sun's cycle of magnetism because that's what I do for my research. And right now I'm actually on a NASA panel that convenes every 10 years in order to predict the sun's next upcoming solar cycle. And so I'm on what we call solar cycle 25 prediction panel. And here I am with a bunch of other colleagues a couple of years ago up in the mountains of Colorado for our retreat to think about how we're going to predict the sun's upcoming solar cycle. So we want to predict the sun cycle because those sunspots that we see on the surface of the sun and the number of those spots as they change over time, those are directly related to the sun's magnetism that impacts our solar system. The sun's magnetism as it impacts our solar system is generally what we refer to as space weather. So any sort of activity that the sun does that can impact our solar system in some sort of predictable way is what we refer to as space weather. And we'll talk a little bit more about space weather later. What generates the sun's magnetism? Well, it is a process called a dynamo, which we already learned a little bit about for the Earth. So a dynamo is a mechanism that converts mechanical energy into electric and magnetic energy. In our Earth's interior, that was motion of the liquid metallic outer core. In our sun, it's motion of the hot gas that the sun is made up of that creates magnetic fields. The study of dynamo activity is linked to what we call magnetohydrodynamics. Magnetohydrodynamics is the combination of the study of magnetism with the study of fluid motion, which is hydrodynamics. So we think about the sun's interior as being a fluid, because gas behaves like a fluid. In order to have a dynamo, you have to have fluids with high electrical conductivity. Basically, you have to have a fluid where electrons are free to move within that fluid. In the sun, that's the hot gas that the sun is made of. In Jupiter and Saturn, it's their outer atmospheres that are under such extreme pressure and temperature that that gas behaves like it's an electrically conducting fluid. In the interior of a planet like the Earth, we've got our liquid metallic outer core, or you could have an ionic fluid in the interior of a planet like we have out for Uranus and Neptune. So essentially what that means is that you have a fluid that is not, the constituent components of that fluid are not electrically neutral. They have some charge on them, and then those fluids can spin around as a product. They can generate an electric field, and as a byproduct, a magnetic field. And then once you have that fluid with high electrical conductivity, you have to have motion of that fluid. You have spinning of the planet or star, You've got convection, which is the motion of that fluid inside the planet or star. That material is warm, so it's rising and then it's turning over, and it's because it's cold, and you get these giant convective patterns. Or you can have shear. Shear is what happens when you have two layers moving at different speeds or in different directions that go past each other. So any of those things in combination or happening inside a fluid with high electrical conductivity can give you a dynamo action. Now, the sun has something that we call differential rotation, and a lot of other stars have this too. Differential rotation happens when parts of the star rotate at different speeds. So for the sun material at the sun's equator, the hot gas, the plasma at the sun's equator, is moving faster than the material is up at higher latitudes. And that's what we call differential rotation. Parts of the sun's layers are rotating at different speeds. So for example, material at the sun's equator takes 25 days to go around the sun once. But material up near the poles take about 30 days to go around the sun once. So the sun's average rotation is about a month. But the material at the equator of the sun is rotating much faster than material closer to the poles. So everything between the equator and the pole, things are moving faster at the equator, and then as you increase in latitude, they're rotating around at a slower rate. This is the question that I'm going to ask you for this engagement check. One way to track the sun's rotation, or as we observe other stars, we do this too, is by monitoring how long it takes a sunspot to rotate across the solar disk at different latitudes. So thinking about what we just talked about sunspots and what we just talked about with differential rotation, how fast should a sunspot rotate if that sunspot appears at the equator and we assume it's moving at the same rate as the material at the equator, okay? And then, would sunspots at higher or lower latitudes appear to rotate more quickly? Why? Part of my research is to use computer simulations to study how the sun and other stars create their magnetic fields, using these large computer simulations where we put in the equations of magnetohydrodynamics for particular stars and see what happens. So this is a simulation of a dynamo for a rapidly rotating star like the sun. This is not my simulation. This is a simulation by an astronomer called Ben Brown. And let me play this again. Okay, so all these little spaghetti lines, those are lines of magnetism. The red directions, the magnetic field is pointing in one direction. In blue, the magnetic field is pointing in another direction. So as the star rotates, in the plasma, the fluid the star is made up of convects and moves and spins, you generate a magnetic field. And this magnetic field changes over time. And so we're seeing that the polarity of these magnetic field lines are changing over time. So this slide is essentially a summary of the work that I did to get my PhD. And I did computer simulations to study how the sun gets its spots. And we think this is how other stars might get their spots too, because we know that other stars have star spots. It's not just the sun that has sunspots. So what happens is that bundles of magnetism created by the sun's dynamo are going to rise through the sun's interior, intersect with the surface to form sunspots. So what we have here in gray is the top of the sun's radiative interior layer. And this upper shell here, that's the sun's convection zone. That's the region where the plasma and the sun's outer layers is getting warm at the bottom, rising to the top and cooling off. These blue regions are cooler regions where the material is going back down towards the sun's interior. These red regions are where the material is rising up towards the sun's surface. And this green band here, that's a giant band of magnetism that's going to rise to the sun's surface. Okay, so let's see what happens. So we see that the sun's outer layers, because they're convecting, because they're moving around, it's going to jostle around these bands of magnetism inside the sun a little bit. And then some of that material that's rising up to the sun's surface inside the convection zone is going to pick up some parts of this band of magnetism, and it's going to bring that part of the magnetic band towards the surface. And also the magnetic band is a little bit less dense than the surrounding material, so it wants to pop up to the sun's surface too a little bit, kind of like when you have a balloon filled with helium and you let it go in the atmosphere. So right here, we've got one of these bands of magnetism that eventually made its way to the top of the sun's convection zone, and right there is where you would expect to find a sunspot.